Intrusion detection systems, or IDS, have long relied on traditional signature-based techniques. These work well for known threats but fail to detect new or modified attack patterns. In today's landscape, cyber attacks are becoming increasingly evasive. They encrypt payloads, mimic legitimate behavior, and often slip past static rules. Machine learning offers a more adaptive solution. It can detect anomalies and patterns without relying on predefined attack signatures, which makes it highly suitable for modern network security. The aim of my project is to evaluate multiple machine learning models for binary intrusion detection. I use the UNSW NB15 dataset, a modern dataset that includes realistic traffic with labeled attack instances. The goal is to identify which models are not only accurate but also practical for deployment in real-time network environments. Prior work highlights the limitations of static IDS tools. Iluena point out that they lack adaptability to evolving threats. Studies by Zhang and Yin show that machine learning models, particularly random forest, SVM, and neural networks, outperform traditional systems on benchmarks datasets. Despite these advances, existing research often overlook practical deployment challenges, such as real-time performance, explainability, and modern retraining needs. I use the UNSW NB15 dataset, which was created using IXIA Perfect Storm tool. It simulates real and malicious network traffic and contains over 260,000 records with 45 features. The classification task was binary, normal versus attack traffic. This figure shows the class distribution in the training set. As you can see, the dataset is imbalanced. Normal traffic makes up a majority of the records. This imbalance is important because it influences how we evaluate in model performance. Metrics like recall and F1 score become more important than raw accuracy. Before training any model, I removed any non-predictive fields like ID and attack cat. So categorical variables such as protocol and service types were label encoded. I also scaled the data and dropped features with a Pearson correlation above 0.98 to reduce redundancy and noise. I tested 6 supervised models: random forest, SVM, k-nearest neighbors, naive Bayes, decision tree, and multi-layer perceptron. The evaluation focused on accuracy, precision, recall, F1 score, and training time. All models were implemented in Python using scikit-learn and trained in Google Colab for efficient computation. Among the 6 models, random forest achieved the best overall performance with an accuracy of 87.1% and an F1 score of 86.8. The MLP and decision tree also performed well, though MLP took longer to train. Naive Bayes was the weakest performer, particularly in precision and recall. This table summarizes the metrics across all models. Random forest balances strong performance with fast training time, which makes it a good candidate for real-time applications. SVM, while accurate, had a much higher training cost, and KNN showed scaling issues. I generated confusion matrices for the top 3 models: random forest, decision tree, and KNN. These matrices give us a clearer picture of false positives and false negatives, which are critical when evaluating IDS. As we can see here, random forest has high true positives and low false negatives, which is ideal. The decision tree has more false negatives, meaning it misses more attacks. KNN sits somewhere in between, showing a conservative classification pattern that may produce more false alarms. I also evaluated ROC curves, which show the trade-off between true positive rate and false positive rate at various thresholds. The ROC curve for random forest rises steeply towards the top left corner, and its area under curve is 0.98. This confirms that the model performs exceptionally well in separating malicious from benign traffic. To explore the dataset structure beyond labels, I used PCA to reduce dimensionality and apply k-means clustering. This helped visualize whether the malicious traffic and normal traffic naturally form separate groups. This scatter plot shows the PCA reduced dataset with 2 clusters identified by k-means. We can see a strong separation between the 2 groups, which support the effectiveness of the feature set and validates our classification results. In conclusion, random forest proved to be the most practical model for IDS, delivering high accuracy, fast training, and solid interpretability. For future work, I plan to explore multi-class classification to detect specific types of attacks like DOS or exploits. Other directions include incorporating time-based features, testing adversarial robustness, and building hybrid systems that combine supervised and unsupervised model for enhancing adaptability, as well as trying out different data sets in the future with more with real-time applications. Thank you.